electromagnetic waves. So most of this, like the major part of this chapter is basically a self-study topics, like it has self-studies topics. So I'll tell you what all you have to study on your own and memorize on your own, but whatever is the understanding part that we'll discuss here. So we'll start with understanding what a displacement current is. So in fact, let me make a circuit here where, for example, I have a capacitor. I connect this capacitor to a resistor and then I connect these to a cell. As you know, it's an RC circuit where initially there will be charge flow. So if it has a value R, the resistance has a value R, battery has a EMF E, and then capacitor has a capacitance C. So you know that current will start flowing, it will start charging the capacitor. Initially the entire V will be just on what do you say, the R, because initially it will be as if it's an open wire. When a capacitor is uncharged, it will be an open wire, so current would flow. Slowly the value of current will keep decreasing, and then at infinite time or at steady state, the capacitor will be fully charged, and then I can actually break this circuit and I will say V is entirely dropped on C, and then the potential drop on R will be 0. So initially V was completely on 0, the drop was completely on R initially, and then exponentially the potential difference actually dropped completely onto C after infinite time. So or what you could say is the steady state. So but in between V being completely on this and V being completely on this at the steady state, in between t equal to 0 to infinity, there was charge flow, right? There was current in this circuit. So in fact, wherever there is current flow, we've already seen Amperes law. We can apply Amperes law. So in fact, at a general time t, let current be I of t. You already know what I of t is. It is nothing but V by R times e power minus t by RC, the formula from the RC circuit's formula, a charging capacitor. This is the case of a charging capacitor. So here I can take an open surface which is nothing but this plane area, like this circle. Let this can be my open surface here. If the current which is entering this surface be I of t, you already know, taking Amperes law, taking the line integral of magnetic field around the boundary of this open surface, I can say that integral B dl will be nothing but mu naught times I of t, right? And because if it has only one turn, my n will be equal to 1. Otherwise, the complete law is mu naught ni, where the surface, like the boundary will have n terms. So like every turn will behave as a loop, and all those loops, n loops, will add up to the line integral of this. So your open surface is this, and then this is the boundary. So in fact, I can assume that the magnetic field around this, because it's a circular, it's just like a wire. It's just like a wire, and around which I want to calculate what the magnetic field is. So I know it's always constant around a wire. So I can take this out of the integral, and then I can write integral dl is basically the length of the boundary, which is nothing but 2 pi r. Let the radius be r. So b times 2 pi r is nothing but mu naught times I of t. So you have to understand here, because your electric field will keep your current will keep changing with time, B will keep changing with time, but it will have a value according to this particular, if I assume this as my open surface. Now in fact, I'll draw another similar diagram here. And then the same capacitor, the same resistor, the same battery, everything is the same here. The current is still flowing. The current flowing is IT, which has the same formula. What I'll do is I'll now take a different surface. So now my surface, I should still take an open surface. Let my surface be this jug. Okay, let the surface be your jug. So as you already know, in Amperes law, if I have this jug here, and I were to calculate the line integral of electric field around this, line integral of magnetic field around this boundary, around the boundary of this open surface. This is an open surface, right? Because it's not completely closed. Just the way this is an open surface, this also is an open surface. So the current piercing through, the current has to pierce through the surface. If the net current piercing through the surface is I, like this, and then anything going out, let that be minus I, let this be I1, let anything going out be minus I2. Like the sum of the net current, I can say, is integral B times dl around this boundary. I can integrate this, and I can say that according to Amperes law, this is nothing but mu naught times, if the surface then turns, I net, right? Where I net is the sum of the current going in and going out, like with their signs. If you take currents going in as positive, you have to take currents going out as negative, and then you have to add them accordingly. But you have to remember that each of this current has to pierce the surface. So like this jug is a hollow one, and your surface is this. So your current has to pierce the surface, and only then such currents you can apply in the law, right? So in this case, this was my surface, like this circular disc itself was my surface, the open surface, and the current is piercing through this. But now the surface that I have taken, this part is hollow, the circular part is hollow. This is my surface, so the current has to pierce through that. Whatever the current pierces through that, only that I can use here, and I can equate it to integral B dot dl. So I hope you have understood this current piercing the surface concept. Only these currents which pierce the surface can be used in this formula. So here, so now let's come to this. As you can see, this IT comes here, and this IT charges this capacitor. But the cases that we have seen now, we don't see any current inside this, right? So it's like in this jug here, IT comes until this place and stops, right? Here it stops. This is your IT. It comes to this place and stops. It's not piercing through the surface, right? In fact, I cannot see any current right now which is piercing this surface. If there is no current piercing the surface, and I want to calculate the line integral of magnetic field around this, I will say integral B dl is nothing but mu naught times, if it has only one turn, n equal to 1, times 0. Why 0? Because there is no current piercing through the surface. So in turn it will give me that the magnetic field is 0, like in this case. But in this case, for a similar boundary, I'm getting I'm getting some value for magnetic field. So like, why is this contradiction happening when I change my surface? That is because this form of Amperes law is not the complete form actually. So here we'll actually derive the complete form now. First deriving what is known as a displacement current here. So in fact, let Qt be the charge on the capacitor right now. So let it be Q of t. So as you know, Q is changing with time. So I already know that Q as a function of time is nothing but Q, see, when the entire potential comes on this, the maximum charge will be CV. So it's nothing but CV times 1 minus e power minus t by RC. So these formulas you already know from your basically the RC circuit. So this is the charge on the capacitor. So let me calculate the electric field in the capacitor at a time t. So you have electric field inside this capacitor. So it depends on charge, as you know. So electric field as a function of time t is nothing but sigma of the plates. So this plate has a plus sigma, that has a minus sigma. This is Qt, this is minus Qt. So sigma of the plate by epsilon naught, this we already know. Because charge is changing with time, sigma also will change with time. So in fact I should write sigma of time here. And then this is nothing but my Q of t by area of the plates times epsilon naught. This is my electric field as a function of time. Right. Now you also know if I take a surface inside this, what do you say, inside these capacitors, any surface which has the same, you have a plate here, you have a plate here, you take a surface inside this such that it has the same area as the plates, right? If the plates are rectangles, your surface also is a rectangle which has the same area as the plates. Now I can say that the flux through this surface, which has the same area of the plate as to what the plates are, is you know the formula for flux is E dot ds. This is what your flux is through the surface. Value of electric field does not change with length here because this thickness is very small compared to the length of the plates, and also it's so uniform that at each of the points here at the area that we have taken, every point the electric field value will have the same value. So in fact I can take it out of the integral and I can say that this will be equal to E times integral ds, like ds, the surface that we have taken, any small area will be ds, electric field will be the same for all of these ds's, and then you have to add them, it will add up to the area of the surface, that is basically the area of the plate that we saw. So I can say that the flux through the surfaces, take the A there, and then I will say flux through surface, which is nothing but phi. Phi will be a function of time because when you multiply A there, Et times A will be nothing but Qt by epsilon naught, right? And because charge is a function of time, flux also will be a function of time. So in fact, if I differentiate this flux with time, if I do d phi, so let me write it here, if I do d phi of t by dt, so understand how I started the proceedings. I first calculated the electric field which is in between these, that will change with time because charge is changing with time and electric field depends on charge. Now I calculated the flux due to this electric field, that also will be a function of time, and now I'm differentiating the flux as a function of time. So that's how we have gone ahead. So differentiated with time, you will have 1 by epsilon naughts dqt by dt, which is nothing but your it. So like rate of change of this charge is nothing but this it, right? If you differentiate this with time, you'll get what is you'll get it basically. So this it d phi of t by dt, this it is what is your displacement current. So in fact now I should modify Amperes law to this: integral b dl is equals to mu naught times n times it if the boundary has n turns, plus I should also include this displacement, the displacement current here. So this is nothing but epsilon naught times d phi of t by dt. Let me just verify this. Epsilon naught times d phi dt is the current, right? Is the current. So you have to multiply mu naught times n to the current. So in fact, let me rewrite it properly. Integral b dl is nothing but, you could say, mu naught times n times I conduction plus I displacement. What does this mean? And as you know, displacement current has the value this. So let's try to understand this. This conduction current is nothing but the current which actually, like you can very easily visualize it, which pierces through the surface. All those currents are nothing but your conduction currents. Sometimes when these conduction currents are not present, it looks as if there is no current. So it looks as if there is no current going through this. It looks as if this IT has stopped and there is no current piercing this. But there is a displacement current which is not visible here, which is actually existent to ensure that this Amperes law holds good. So this Amperes law has to be consistent whether you take this surface, the value of the magnetic field that you get here has to be the same here. So Amperes law has to be consistent. To make it consistent, this displacement current, which you initially thought was absent, is actually present. So the value of this displacement current is IT. In fact, here you can see this, you can see, what you can see here is the current that is going here, is the same current, like this IT itself is the same current which is piercing this surface. So because you got the displacement current value right, the current inside this capacitor, due to this changing electric field, E is changing with time. So because E is changing with time, the current that is produced inside this capacitor, which is called your displacement current, so I displacement. In fact, in course of deriving this displacement current, we actually derived that displacement current is nothing but the current which was actually outside. So in fact, you can say displacement current inside the capacitor is the current in the circuit. So both of them are the same. And then why should displacement current exist? It exists to make sure that Amperes law is consistent for both these surfaces and for any surface for that matter. So remember the formula for displacement current. Remember that displacement current is equal to the current in the circuit which is there right now, and remember that displacement current exists so that I get the complete form of Amperes law, so that Amperes law is consistent for all surfaces. So the mistake that I did here was I just wrote this, but this is the current, right? You have to multiply mu naught to the current. So you are multiplying mu naught to current here. You have to multiply mu naught to this current also, like that will make the law complete. So this is the Amperes law in its complete form. And then because I'm just taking a surface or a boundary with one turn, this n is 1 basically for my case. Sometimes when you have like you take a surface which is rolled around n times, you'll have to have an n there. So this is what your displacement current was, why it exists, and now let's proceed with the further topics in the chapter. Maxwell's equations, in fact we've already seen them before. This is basically your Gauss law for electricity, where electric flux through a surface is nothing but, which is given by this line area surface integral of electric field. It's nothing but equal to the charge enclosed inside the surface by epsilon naught. And then this comes from the chapter magnetism, Gauss law for magnetism, where surface integral for magnetic field is equal to 0. Why is it 0? Because you take any surface, if you have a north pole, you will have a corresponding south pole inside the surface, because it's like if there is a plus 1 in charges, if there is a plus 1 coulomb charge, it's not necessary that you should have a negative charge also. Like it's not necessary that you have a minus 1 coulomb charge or any negative charge. But as you know, in magnetism, monopoles do not exist. So if there is one north pole, there has to be one south pole. It's like saying if there is one plus 5 coulomb, there has to be a minus 5 coulomb. It's like saying that. So ultimately the net magnetic monopoles add up to 0, because for every north pole there is a south pole, and then magnetic poles inside will be 0. So that's why this areal integral is 0. This is Gauss law for magnetism. And then this is line integral of electric field, which is equal to the negative of the change of flux with time, of the magnetic flux with time. This is Faraday's law that comes from the chapter electromagnetic induction. And then here you have Amperes law. Basically this is Amperes law, and we have discussed it in its full form here. Why am I mentioning the word, like why am I emphasizing on the full form? Because we tend to just use mu naught times n times I conduction so if you have an open surface, if you want to calculate magnetic line of magnetic field around line integral of magnetic field around the boundary, you calculate how many currents are piercing through the surface and then add and subtract them according to if they are going inside or coming out. That actually becomes your net conduction current. But then we tend to forget about this displacement current. So in fact this displacement current exists to make sure that Amperes law is consistent for every surface. So that's why this is Amperes law in its full form. So remember these 4 equations. We'll now understand what electromagnetic waves are and how are they produced. So in fact I'll explain it to you in a very short manner. If you have a charge, if it's at rest, it only produces electrostatic fields, right, that we saw in the chapter electrostatics. You also know the formula for calculating an electric field at a distance r. So that particular electric field was your electrostatic field because your charge was at rest. Even if your charge is moving with constant velocity, that also doesn't make a difference. But if your charge is accelerating, if your charge accelerates, then these electromagnetic waves are produced. So these are produced by accelerated charges. So remember this. In fact, charges here produce, these accelerated charges produced oscillating electric fields, oscillating electric fields become a source for oscillating magnetic fields, and these oscillating magnetic fields become a source of oscillating electric fields. So it happens that way, that accelerated charges produce both of these, and then these in turn keep producing each other, right? So an oscillating electric field produces an oscillating magnetic field, and that oscillating magnetic field produces another oscillating electric field. This oscillating electric field produces another magnetic field, oscillating magnetic field. So it keeps going on that way, and that's how this entire electromagnetic wave is produced. And then, as goes by the name, it has a component of an oscillating electric field, electro, and it has a component of an oscillating magnetic field. So in fact, you can visualize it this way. So if this is your x-axis, if this is your y-axis, and this is your z-axis, if I say that electric field is oscillating in the x, so usually the electric fields in the electromagnetic fields are sinusoidal oscillating fields. So let your electric field oscillate in the x direction. So in fact I can say here that let this be your electric field. Let me use a different color actually. So this is your electric field, E. In fact, I can write any wave of this form. I can write, because this E, it's actually moving up and down in the x direction, right? So I can write it as Ex, because in this wave, if I put a coordinate for x, I should get the value for E. So in fact, I'll write this as Ex is equal to E naught times sine kx minus omega t. This is just like another wave which has a wave number k and which has an oscillating frequency omega, and then for different values of x and different time that you put, you'll get different values of Ex. So that will give you the value of electric field for a particular x at a particular time. So this is the complete wave equation. In turn, your what do you say, magnetic field, the oscillating, these oscillating electric fields give rise to oscillating magnetic fields, and your oscillating magnetic fields oscillate in a plane which is perpendicular to the electric field. So electric field is oscillating about, or you could say it's moving about x-axis like this, and then the magnetic field which is along your y direction, you can say it as B naught times sine kx minus omega t. So everything is the same. In fact, this is your ideal electromagnetic wave, you could say, where E naught is the maximum value, the amplitude of the electric field that is there. So the maximum value of E naught, the maximum value of the electric field for any given x at any given time is E naught. So similarly, that is what B naught is, the amplitude of the magnetic field. So this is the magnetic field, maximum magnetic field possible. So as you can see, your x is oscillating, E is oscillating in the x direction, B is oscillating in the y direction, and the motion of wave, basically the motion of the wave is actually perpendicular to both of these. So in fact, how if you want the velocity, if you want the velocity of the if you want the direction of the motion of the wave, the direction of motion of the wave is, or I can say direction of wave propagation is, propagation is given by E bar cross B bar. So I'm saying that the direction of wave propagation is given by E bar cross B bar. What it means is, if you take the cross product, so E is all your electric field is in the x direction. So electric field, I will say, is in the I direction in this case. And then what do you say? Magnetic field is in the j direction here, y direction. So if I take the cross product of these two, I'll get k. So I can say that my wave, the electromagnetic wave, is moving in the k direction. That means in the z direction. So in this example, Your electric field is oscillating in this direction, your magnetic field is oscillating in this direction, but your electromagnetic wave is moving in the z direction, in a direction which is perpendicular to both of them. And the velocity of the wave, which is denoted by c here, is given by E naught by B naught. So the ratio of the amplitudes of the electric and the magnetic fields is basically the direction of the velocity of your electromagnetic waves. And usually a light is also an electromagnetic wave, so c is basically the velocity of light here. So a light actually has oscillating electric fields and oscillating magnetic fields, and then when you put the value, you'll get the velocity for this particular wave. So this is how electromagnetic waves are produced, they are propagated, and these are the formulas you are supposed to remember. Remember that all of them carry energy, right? Any wave for that matter, any wave carries energy. So these waves also carry energy. So we'll see when these waves strike a surface, they also carry energy, they also carry momentum. So they transfer some momentum to the surface that they strike. So we'll see the formula for all that, and then we'll just discuss in brief what electromagnetic spectrum is, and then with that I'll leave you with the topics of self-study. So let's proceed.